Alright, this is parts 2 and 3 from the Module 4 example 1. We need to determine what the charge and voltage across each capacitor is. So to do this, we're going to use Q is equal to CV. This is true for real and effective capacitors. And what we need to do is reduce this circuit down to one or more effective capacitors that are connected in parallel to the EMF, and then start working backwards. So for example, this circuit here is capacitor 1 and an effective capacitor that represents 2, 3, 4, and 5, both connected in parallel to the EMF. So that's where I'm going to start. So I can write down what the voltage across capacitor 1 is immediately. It's equal to the EMF voltage, which is 10 volts. Which means I could calculate what the charge on capacitor 1 is. And it's going to be 10 microcoulombs. Now I'm going to calculate what the charge on that effective capacitor 2, 3, 4, and 5 is, because the voltage across that capacitor is again equal to the EMF, which is 10 volts. So the charge is going to be its capacitance, this is the effective capacitance, times the voltage. The effective capacitance for that capacitor is actually written right here, 2.43 microfarads, so this is going to be 24.3 microcoulomb. So now I need to work backwards. I need to start unpacking these effective capacitors. So this effective capacitor C2, 3, 4, and 5 was created by combining capacitors 4 and an effective capacitor 2, 3, 5 that were in series. So I'm going to unpack this this effective capacitor into those two. So here's C1, here's C4, here's C2, 3, 4, 5, or excuse me, 2, 3, 5. So the thing that I need to know when I unpack an effective capacitor into two or more capacitors is that when they're in series, the charge on each capacitor is the same as the charge on the effective capacitor. That's an easy an easy mistake to make, is to try to divide this charge by 2 or some ratio, and you don't need to do that. So what I'm saying here is that the charge on capacitor 4 is equal to 24.3 microcoulomb. It's not equal to half of that 24.3 or some ratio, some fraction of that 24.3. So I calculate what this charge here is on the effective capacitor. When I break up the capacitor into two capacitors that are in series, the charge on each is the same. So that means that the charge on 2, 3, 5 is also equal to 24.3 microcoulomb. So now I can calculate what the voltage across capacitor 4 is, because it's going to be equal to the charge on capacitor 4 divided by its capacitance. And the capacitance of capacitor 4 is 4 microfarad. So that's going to be 6.08 volts. I need to calculate what the voltage across this effective capacitor is, because the effective capacitor 235 represents a couple of capacitors that were connected in parallel, and when I unpack this effective capacitor into those two that are in parallel, the voltage across the effective capacitor will be the same as the voltage across each of the capacitors in parallel. So the voltage 235 is going to be equal to the charge divided by its capacitance. So that's the 24.3 microcoulombs divided by the effective capacitance for 2, 3, and 5. I need to go back up and find that effective capacitance for 2, 3, and 5. Here it is, C235. That is 6.2 microfarad. and I get 3.92 volts. So these two voltages should add together to give me 10. Right, so the voltage across 4 and this effective capacitor should be equal to the EMF voltage. And if you add those two together, you get 10. Alright, so now I'm going to unpack this 235 into two capacitors that are in parallel. So there's C1, here's C4. This is 2 and 3 together, and then this is 5. 1, 4, 5, 2 and 3 together. So the voltage across capacitor 5 is just equal to the voltage that was across 235 effective capacitor. So that's 3.92 volts, which means that the charge the charge on 5 is just going to be its capacitance times the voltage across it. And the capacitance of 5 is 5 microfarad. So this is going to be 19.6 microcoulomb. The voltage across the effective capacitor 2,3 is the same since they're in parallel, so that's 3.92. Which means that the charge on that effective capacitor can be calculated. The effective capacitance for 2 and 3 I need now. That was the first one that we calculated. Should be up at the very top here. Effective capacitance for 2 and 3 is 1.2 microfarad. I get 4.70 microcoulombs. And finally, that effective capacitor for 2 and 3 represented two capacitors that were connected in series. So I'm going to unpack those. My circuit diagrams are getting worse and worse. So here's 2, 3, 4, and 1. So I know already that the charge on 2 is equal to the charge on 3, which is equal to the charge on the effective capacitor. I do not divide by 2. So that's going to be 4.70 microcoulomb. That means that the voltage across 2 is just Q2 over C2. And C2 was 2 microfarads. So the voltage is going to be 2.35 volts. And V3 is going to be its charge. Oh, that was a bad 3. Its charge divided by C3. C3 was 3 microfarads. I get 1.57 volts. And there we are. We've got the voltage and the charge for all of these capacitors. So again, you need to start with a set of effective capacitors that are all connected in parallel, and then work backwards, unpacking the effective capacitors into their actual capacitors. If an effective capacitor represents capacitors that are in series, then the charge on that effective capacitor is the same as the charge on the capacitors that are in series. If the effective capacitor represents capacitors in parallel, then it's the voltage that's the same.